So our next panelist is Douglas Dreger. Doug is a professor of geophysics in the Department of Earth and Planetary Science, and he has been working on an early warning system for earthquakes in California. I think we have all been inspired by the videos of the early warning system in Japan in action, warning some people in some regions as much as a minute before the shaking came. And so Doug will be able to tell us whether a system like that is feasible here in California and what it would take to build it.
Thank you, David. Actually, I haven't been working on an earthquake early warning system, but Professor Allen in our department has been, and so I'll be showing some of his work. One of the things that I've been working on is trying to learn a little bit about methods where we might be able to get a tsunami early warning capability, looking at low-frequency wave fields. So I'll also touch on that. But echoing Roland's comment regarding this earthquake and the movie that he showed, showing probably order of 1,000 continuous GPS sites and that data set that showed those large static offsets, that this earthquake is the most complete near-field data set recorded for a great earthquake. And this is a really important point. And there's more than 1,000 strong motion stations that have recorded this event. And from these data, there's much that we can learn from it, including the process of the rupture. And this is a list of analyses that will take place in the days and weeks and months and years from this point forward. But looking at the process of fault rupture, physics of wave propagation, importantly, the nature of the strong ground motions. We're going to learn a lot about that, how to better prepare, utilize these strong ground motions. And finally, the main point of this presentation, which is how to provide shaking and tsunami hazard warnings in future earthquakes. So this is a map that shows the distribution of these seismic stations that are used for the early warning system in Japan that Professor Allen prepared. And given a suitable network, warnings of imminent strong shaking and tsunami are possible because of the physics of the problem, that the speed at which P waves and S waves travel are vastly different. The speed at which tsunami waves travel is much slower than seismic waves. So if there's some technique that allows you to analyze a P wave that's traveling at 14,000 miles per hour and to be able to learn something intrinsic to the source of that event, then you could, in other words, if it's a large event, then you have some time built in simply because the S waves are traveling at 7,000 miles per hour. And the S waves are carrying the damaging ground motions. And the tsunami is only traveling at 500 miles per hour. So there's great potential for early warning in these cases. And so in the case of Japan, the strong shaking and tsunami warnings were successfully issued for this event. And before I go on to that, though, I'd just like to illustrate again this data set that has been collected. And this on the left, there we go, very sensitive. On the left is the peak ground acceleration that was recorded at these sites, color contoured to peak ground acceleration. And I can't, maybe I should put my glasses on, but the maximum acceleration here on the scale is about 2G. The peak acceleration is 2.7G at one of the sites. There's about 10 stations that recorded greater than 1G. But one of the messages that comes out from this earthquake is that the vast majority of observations for this event have peak ground acceleration and peak ground velocity, which is shown on the left, that are consistent with our prior experience. So the levels of peak ground acceleration and velocity are what we've seen before. But one thing that's atypical in this event is this 500 by 100 square kilometer area where there was ground accelerations exceeding 1/10 of 1G. And so that's a huge area, but that owes to the spatial dimensions of the source. The other interesting thing about these data, which is atypical, is the duration of the record. So I don't think you can see this, but this is 100 seconds, 200 seconds, and 300 seconds. So about 5 minutes of record shown here. And these are some strong motion records. All of the peak accelerations are less than 1G. What really struck me about these observations is that there's two primary envelopes or packets of energy that are likely related to heterogeneity or complexity in the source. So this is one slip model that's been produced for this event. It shows that there are 3 slip patches, and energy radiating, very sensitive, energy radiating from each of these slip patches contributes to these bundles of energy or wave packets that we observe in the strong motion records. This is a slide that Professor Allen prepared illustrating the capability of early warning in Japan. The Japan Meteorological Agency has been issuing earthquake warnings since October 2007. They make use of 1,000 seismic stations across the map shown. And the important point here is about 5.4 seconds after the first detection of a P wave on an onshore station, an estimate of the ongoing earthquake was produced, and the software was analyzing whether or not there was an earthquake and preparing to issue a warning. About 8 seconds after the P wave, this warning was issued. And so this contour is showing the S wave, and the next one out is showing 5 seconds of warning. So the closest point of land would receive 5 seconds of warning from the greatest shaking. The other thing that you can take from this map is there's between 25 to 30 seconds at the most distant regions of the map where the strong shaking occurs. Tokyo, which is off the map, would receive more than a minute of early warning from the strong shaking. In terms of tsunamis, this is a map that shows tide gauge records at stations that are closest to the source. The earthquake occurred here, origin time 1446-23. You can see there's some small deviations from the flat line at the red curve that comes before the first tsunami alert, which was issued about 3 minutes after the earthquake. There's really not much you can do in terms of a warning when you're right next to the ruptured fault. You're going to have elastic deformations, the ones that Roland showed with or Professor Bergman showed with the GPS, and if you have deformation at the coastline, you're going to have immediate inundation. But what this is also showing is that there's between a 20 to 30 minute delay before the onset of the truly large tsunami waves, damaging waves. So coming back to California, can great earthquakes and tsunami occur here? And the answer is yes. As Professor Bergman pointed out, the Cascadia subduction zone can produce magnitude 8, 9 earthquakes. There's been 7 events in the last 3,500 years. Average recurrence intervals are between 250 to 900 years. The last great event was on January 17th. I think it was January 26th. January 26, 1700. This is based on tsunami records from Japan and back projection of tsunami waves across the Pacific Ocean. The geometries between the subduction zone and the coastline are very similar to the case in Japan, in that the tsunami wave arrival times would be between maybe 10 to 30 minutes. It depends. Obviously here at Cape Mendocino it would be earlier than if the dislocation was further north on the Cascadia subduction zone. One of the things that we're working on at Berkeley, as I mentioned, is a method to try to autonomously detect and locate and determine magnitude within 8 minutes of these great earthquakes that may hopefully feed into tsunami early warning capability in the future. In terms of earthquake early warning or strong shaking early warning, this is a slide that Professor Allen prepared. Professor Allen is working with a group of colleagues at Caltech and the USGS and the Swiss Seismological Survey to evaluate capabilities of earthquake early warning systems. The idea is that these earthquake early warning systems will be received on computer desktops, maybe cell phones. They're working on warnings to a small test user group this year. An important aspect of this has been the upgrade of the seismic stations, which was made possible through the American Recovery Act, the ARA funding, that was used to improve our instrumentation capabilities and reduce transit times for seismic data. Professor Allen's been proposing implementation of a Japanese-type public statewide system. It'll take about 5 years to implement, $80 million, and he has concern about the current federal budget crisis, and it threatens, it possibly threatens our capability to move earthquake early warning forward into the future. Thank you.